Hello everyone. So this is a video I decided to do for this following reason. When you type in the internet, especially YouTube, when you're interested in a subject, and in my case it was about total cross-section, when you type it on YouTube, this is the kind of result you can expect. Okay, especially if you're interested in total cross-section in the context of electron scattering. So you get scattering cross-section here, principle of superposition, easy road cross-section, which is not really what I'm looking for. So nothing about gas interaction. And then the second one, total electron cross-section. I have tried excitation cross-section, electron scattering, but it's very difficult to get exactly an explanation of exactly what does it mean total cross-section. That's why I decided to do this video. So in this video I will give you understand of the concept of total cross-section, which is usually known sigma total. Here. And then I will show you why this quantity, the total cross-section, is useful to get. In the second part, I will present how to determine experimentally the total cross-section. Ideally, as is shown here in this PowerPoint slide, in electron collision with atoms, we would like to send one electron over the gas target and then measure the transmitted electron to know how this transmitted electron was affected by the interaction. And then after several tries, we should get a probability, which is basically a chance, note P, which is a number of time we detected an electron after the interaction with the gas over the number of time we repeated the experiment. And this gives you your probability of interaction. Better said, your probability of your electron not interacting with the gas, and 1 minus that is the probability of the total probability, the probability of any kind of interaction to take place in the gas target. And this is specific normally to each gas. But such experiment is not feasible, although it's not impossible, because the electrons are generally generated by heating of a tungsten filament. For example, it could be done as well by a photoelectric effect or any other kinds, and this causes the liberation of a bunch of electrons, not one. In order to deal now with this issue of a lot of electrons being involved, we had to introduce a new parameter, the flux, or the number of electrons per unit time per unit of area. And this is now the new type of experiment. This is the kind of experiment one has to do in order to get a total cross-section. From this experimental sketch, we can derive a new concept of probability, which is now mathematically not exactly a probability, but still physicists are calling it a probability or total cross-section. So how to get it from this bunch of electrons, which is the electron flux generated by the electron gun. E0 is the beam here, of electron without the presence of the gas in the collision chamber, and you measure it at the detector here when there is, with the detector here, which is a Faraday cap, for example, when the collision chamber is does not contain any gas, and then you get your E0. And then you introduce your gas and you measure this attenuation of the beam after introduction of the gas target. Usually you introduce tens of millitorr, not more. L here is the length of the collision chamber, and N is the number of atoms per unit volume, which is called the molecular density, and it's usually measured by a barometron or manometer. This is just an apparatus you put in your system and it gives you the data basically. So in order to derive now the probability of the electron beam to interact with the gas, in order to derive the probability of the electron, which is E0, to interact with the gas target, we focus on a very small portion. To make it simple, let's say DL, which is nothing else but the differential of the collision chamber. Hence, the total cross-section, the new kind of probability we're facing, is known now from the following relation, which is the small portion of the scattered electron beam, DDS, is just a fraction of the electron here coming and being affected or perturbed by the number of molecular density contained in this small DDL, which is just a small fraction along this length, along this width, I would say. Yes, so basically this is just a fraction. This is sigma total is just basically the fraction of E0, which is incident electron being scattered. It's just that measure, and this is specific to a gas as well. It appears right away that the integration over the whole length of the collision chamber provides the exponential term contained in the total cross-section, as you can see here, and hence you can get your what is called sometimes Bell number law, where you have n, where you have all your parameters which you can get. So E0 is the primary beam now, which you measured when there was no gas. P is basically the law, the ideal gas law, and KT, from which n is the number of density of atom, could be derived. So KT is a constant Boltzmann constant, and T is the temperature. The total cross-section is basically gives you so the total cross-section gives the probability of electron to interact with the gas, whatever the type of interaction, whatever the angle, since the measure is basically an average over the whole solid angle. Cross-section from this electron energy loss spectra. So the principle of any experiment which measures the total cross-section is very simple. You have to send a beam of electron on a gas target, then you have to detect those electrons as a function of energy. To do so, in my PhD, for example, I use an electron gun attached to a hemispherical analyzer, which is basically an hemispherical condensator, which acts like a monochromator in order to narrow the electron beam in order to get a high resolution. A second hemispherical analyzer, which is here, placed after the collision chamber, which is the gas cell here, And the goal is here to collect the scattered electron as a function of energy. And we control the analyzer by starting at a given energy from a computer in a remote mode, V initial to V final, and hence the primary elastic beam is covered up to 100 eV. So you start, basically you're sweeping from a start, let's just say 100 eV up to 0 eV. You're decreasing, and then you cover all the range to get all the scattered electron in this energy range. So the detector, the final detector we decided to use is a microchannel plate, which is here MCP, and I will show you a picture of what it looks like. So this is basically in reality my system, which is used at CSIC, Institute of Fundamental Physics, and their PhD is supervised by Professor Gustavo Garcia. And here is the experiment, which is not completely mounted, but here you have a first part. So the electron gun is here, close to the vacuum turbomolecular pump. Then it sends the electron, which is accelerated by the electron kinetic energy here, and then it's crossing the hemispherical analyzer, which is called here the monochromator because it acts like a monochromator. Then the beam comes until the collision chamber, which is here, contains here, where you can introduce the gas, let's say air, from this valve. You can open here by opening this. Yes, basically by opening this valve here, you can get finally you can introduce a little gas, which you can measure by this apparatus, which is a baratron manometer. And then here you have the gas introduced, and the electron are scattered inside, traversing a nano-hemispherical analyzer, which is an energy analyzer. Then here is a channeltron, but here is a channeltron, which is a, let's just say one single part of a microchannel plate. And here is just electronics, so the preamplifier here, and here you have the divider, and here another turbomolecular pump in order to pump the system and evacuate any gas and have a vacuum, so you can just study the gas inside. You have another vacuum pump, which is just below the system. So one sweep, when you do one sweep, is an electron with the analyzer, gives you